Welcome to the Explainer. Today, we're taking on a genuinely brilliant mathematical tool, and that is logarithms. Now, instead of treating them like some abstract, intimidating set of equations, we're actually going to approach them as a language. Because as you'll see by the end of this Explainer, once you decode this specific language, it completely unlocks the exponential universe around us.
Okay, let's dive right into this. How do we handle massive, exponential numbers without absolutely losing our minds? If you look back historically, way before we had computers in our pockets, astronomers and engineers were basically drowning in manual calculations. They desperately needed a shortcut to make long, multi-step math easy and manageable. And that right there is the exact reason logarithms were invented. Think of them as the ultimate mathematical life hack, designed specifically to save you time. So here's our roadmap for today. First up, we'll establish the real purpose of logarithms. Then we'll translate the language, we'll break down the three core laws, look at working with base 10, and finally, we'll actually measure the mobile signal strength on your smartphone. All right, let's get going. Section 1. The purpose of logarithms. Okay, so logarithms definitely weren't created just to add more pages to your math textbooks. They were deliberately designed to turn massive, messy multiplicative problems into much simpler math. Now, if you read the official definitions straight up, it looks pretty intimidating. It says if a, b, and c are real numbers, where a does not equal 1 and a to the power of b equals c, then b is the logarithm of c at base a. Wow, right? But honestly, all this definition is really doing is rearranging the mathematical furniture. It's just a clever way to isolate that exponent b so we can actually work with it directly. Moving on to Section 2, translating the logarithmic language. I want you to think of exponential form and logarithmic form as two entirely different languages. It's kind of like English and Spanish, but they are saying the exact same sentence. In exponential form, a to the power of b equals c. Now, translated over to logarithmic form, log base a of c equals b. You'll notice the base, a, stays right at the bottom in both versions, but b and c just swap sides of the equal sign. At its core, a logarithm is literally just asking a question. What exponent do I need to raise this base to in order to get this specific result? Now, what's really interesting here is seeing that rule play out with actual numbers. We know 3 to the power of 4 equals 81. In our new logarithm language, that perfectly mirrors over to log base 3 of 81 equals 4. See how those numbers just swapped places? The question log base 3 of 81 is asking is simply, how many times do I multiply 3 by itself to get 81? And the answer is the exponent, which is 4. It's that simple. And this structural translation works flawlessly for decimals and negative exponents too. Taking an example straight from our source material, 2 to the power of negative 3 equals 0.125. Translate that, and you get log base 2 of 0.125 equals negative 3. See? It's the exact same relationship, just dressed up in different clothing. Once you start recognizing this structural pattern, translating back and forth becomes totally automatic. Let's move to Section 3, the three core laws. Right, so now that we know how to translate the basic vocabulary, let's learn the grammar. There are three core mathematical laws here, and they act like simple grammatical rules that help us simplify really complex sentences. We have the product law, the quotient law, and the power law. These three rules are literally the engine that makes logarithms so incredibly useful in advanced science and engineering. Let's de-jargon these rules really quick. The first law, the product law, simply says that when you're multiplying two numbers together, you can just add their individual logarithms. Easy enough. The second law, the quotient law, tells us that when you divide numbers, you subtract their logs. And then the third law, the power law, lets you take an exponent and just drop it right down in front of the log to multiply. So, to recap, multiplication becomes addition, division becomes subtraction, and exponents become simple multiplication. It is a massive calculation lifesaver. Which brings us to Section 4, working with base 10. Let's see how this builds. Up until now, we've talked about base A, base 2, base 3. But there is one base that pretty much rules them all in the practical, everyday world, and that's the number 10. Think about it. Our entire human counting system relies on base 10, so it naturally follows that our logarithms often default to it as well. Because base 10 is everywhere, our source text notes a really helpful standard shortcut. It basically says, if no base is given, the base is always taken as 10. These are known as common logarithms. So if you're working a problem and you just see the text log 100, you can assume there is an invisible 10 sitting right at the bottom. It's automatically asking 10 to what power equals 100. And well, since 10 squared is 100, log 100 is simply 2.
And finally, Section 5, Real-World Mobile Signal Strength.
Now, I promised you earlier that this wasn't just some abstract theory. This decoded mathematical language is literally the hidden foundation of our modern digital lives. When you glance down at the little signal bars at the top of your phone, you're looking at applied logarithms. Mobile signal strength is measured in decibel milliwatts, or dBm for short. And these values range from minus 50 dBm, which is an absolutely excellent signal, all the way down to minus 120 dBm, which is your dreaded, dropped call, very poor signal.
So here's the exact formula that network engineers use to calculate that strength. S equals 10 times log P. In this formula, S is the signal strength we want to find, and P is the raw signal power hitting your phone's internal antenna. Notice how it just says log P? Thanks to that shortcut we just learned, we immediately know it's a base 10 common logarithm because there's no base written out. Okay, let's actually solve a real problem with this. So the crucial point is seeing how these laws cleanly solve for signal strength. Let's find the signal strength S when the signal power P is 1 over 10 to the 6th. Step 1. We convert that fraction into a negative exponent, which makes P equal to 10 to the negative 6th. Step 2. We plug that into our formula, so S equals 10 times the log of 10 to the negative 6. Step 3. We use that awesome third law, the power law, to drop that negative 6 right down to the front. We multiply 10 by negative 6, which cleanly gives us minus 60 dBm. That is an excellent signal, and we completely solved it just by trusting our log laws. And there you have it, the whole shebang. We started with what looked like an intimidating textbook definition, we translated the language, learned the grammar, and we ended up literally calculating the invisible waves connecting our smartphones. Logarithms aren't just arbitrary numbers sitting on a page, they are the absolute key to handling the incredibly massive and the incredibly tiny scales of reality. So I'm going to leave you with this final thought to ponder. The next time you check your phone for a signal or hear about an earthquake measured on the Richter scale, ask yourself, how else does decoded math quietly power the exponential universe around us? Thanks for hanging out and learning with me today on The Explainer.